Hello. Am I audible to all of you?
Yes, ma'am.
Yes.
Yes. Someone is joining. Okay, maybe they are accepting from there. Okay, fine. So I don't have to bother that. Okay, so good evening. Today we'll start our unit 5, which is about the fluorimetry and phosphorimetry. Okay, fluorimetry and phosphorimetry. So to start with, I would like to say you that in our last class we have studied UV visible, IR, Raman spectroscopic methods. Okay, where you find that there is electromagnetic radiation which is falling on the matter is your UV visible and IR region radiation and scattering phenomenon as involved with that radiation. Okay, but in this unit where fluorimetry and phosphorimetry we are dealing with, that time your two more molecular spectroscopic method, fluorescence and phosphorescence comes into picture. Okay, fluorescence and phosphorescence. So these are based on the phenomenon of emission of radiation by electronically excited species and are collectively termed as photoluminescence method. Okay, you people should tune with me from the beginning because after 2 3 like after 5 minutes we'll be discussing a very crucial thing, which if you are able to understand then you can move on smoothly. Otherwise, if there is a lagging behind, there is a gap in understanding, then moving with the fluorescence is very difficult. You will not able to understand. Even the same thing is applicable to any spectroscopic method. Like if you are studying pH metry or conductivimetry, any other analytical tools, you can also follow the book and understand by yourself. But spectroscopic method is a topic which is really difficult to understand of your own until and unless you are not having some hearing impacts. Like if you are listening to me, something you are listening, then you are studying, then it will be easy for you to understand the things. So okay, let's move with this. That here what is happening, there is electronically excited species and are collectively this fluorescence and phosphorescence are known as your photoluminescence method. Okay, so these are radiative relaxation processes that are associated with electronically excited species. Means I was telling you in the last class also, when a molecule is absorbing certain radiation, it is going to the excited state. Then from the excited state, it has to come back to the ground state. How it will come back? By releasing some energy, it will come to the ground state because now it has gone to the off excited state. By absorbing energy, it has to come to ground state by releasing energy. Okay, so it will be followed by the study of relationship of your fluorescence and phosphorescence with chemical structure and the dependence of spectra on the environment of the species. Believe me, this fluorescence is very, very good spectroscopic tool to study the environment around the species. If you are taking a molecule which is fluorescent in nature or phosphorescent in nature, the nearby its environment it can sense very well. Okay, so we'll be discussing everything in detail in this topic in this chapter, that is fluorescence phosphorescence thing. Okay, when this relaxation is accompanied by emission of radiation, it is called luminescence. I was telling you, molecule is going absorbing certain radiation and going to the excited state. That phenomena is your absorption. Then, after it is reaching to the excited state, a relaxation process happens. Either it is radiative or non-radiative. So, this emission of radiation as a whole it is known as your luminescence. And these are of two type. Luminescence phenomena are two type, fluorescence and phosphorescence. In general category, I am talking about phosphorescence and fluorescence. So what is fluorescence? You need to understand this. So fluorescence is the emission of visible light. Remember this one, emission of visible light by a substance that has absorbed light of different wavelength, and the emitted photon has a longer wavelength. Emitted photon has a longer wavelength. Point to be noted. Subsequent parts I will be discussing with you by showing the figures. Okay, the emitted photon has a longer wavelength, and phosphorescence is related to the fluorescence in emitting a photon. However, phosphorescent material doesn't immediately re-emit. It takes time. I am giving you a simple example. You might have seen your what to say in Oriya, I know, but in other language I don't know, where you are just uh, decaying of your bones, and where after the death you are just doing the funerals. Okay, then what happens if you are seeing in villages, you might have heard that you are passing through that way and you are seeing some glowing lights, then people will say, oh, it is so scary, we should not go that way because some radiation is coming out of that. It's nothing but your fluorescence, which we can say the luminescence property of that bones, which is rich in phosphorus, and that is absorbing the radiation, and subsequently with time it is just showing the glowing effect. It is just glowing, and in night time we are able to see that. So from the phosphorus glowing part, this phosphorescence terminology has come. So that is the glowing nature of that bones due to phosphorus. So that is a photoluminescence property. So as this excitation of molecule is due to absorption of a photon, so we can tell this luminescence as to be photoluminescence. I was telling you in the last class, since we are dealing with photon in spectroscopic methods, we can also use photo in any processes like this. Then chemiluminescence is a category of luminescence. It is another phenomena that falls in the category of luminescence, but this refers to emission of radiation during a chemical reaction. Means some chemical reactions are there where you will be seeing a glowing part in that reaction. But remember one thing, if you are seeing a chemical which is color in nature, so it is absorbing and radiating due to different thing, but glowing nature is something different. Fluorescent property is something different. Until and unless it is absorbing some light and emitting, you will not be able to see that. So here is the example of chemiluminescence, the oxidation of luminol. Oxidation of luminol in an alkaline solution is an example of chemiluminescence. So its oxidation of luminol gives you a blue glow. Glowing thing is different, so it gives you a blue glow. This is an example of your chemiluminescence. But this radiative emissions, non-radiative emissions, this all processes you can understand by your Jablonski diagram. This is a very, very important diagram. You need to understand it very carefully. I'm just minimizing the size so that the complete figure will come. Is it okay for you? Is it visible?
Yes, ma'am. Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay. So, radiative and non-radiative processes. Here, if you are understanding this part, that's it. Your fluorescence, phosphorescence will be very easy for you. See, the thing is, we are saying that molecule is absorbing certain radiation, it is going to the upper state. Upper state, we are saying it is going to the upper state. Upper state means which upper state? S1 or S2 or S3. So there are many upper states will be there. But the thing is how much amount of energy the molecule is absorbing, accordingly it will go to the S2 state or S1 state or S3 state like that. But always, so this is one phenomena, that is absorption. It is absorbing certain radiation then going to the excited singlet excited states, that is absorption. And always absorption takes place in which time scale region? 10 to the power minus 15 femtosecond. So the absorption process is so fast. Femtosecond means you can understand. 10 power minus 15, it is so fast. Oh, it is related to some principle also that is known as Planck-Condon principle. I will just discuss with you in later on. So if it is going to the S2 state, it has to come back to the S1 state through your some non-radiative processes, that is internal conversion. Okay, let me divide in this way. There are two type of relaxation happening. One is radiative, another is non-radiative. You are seeing this figure. So in this, radiative transitions are absorption, fluorescence, and phosphorescence. These three are radiative transitions, where it is losing, process is losing light and then it is coming back. However, this internal conversion or intersystem crossing, these vibrational relaxations, these all are non-radiative processes. Mostly the internal conversion, intersystem crossing are non-radiative processes. Means it is relaxation is happening, but through your heat dissipation. No light emission is there. So is that clear? So now we can see. So if it is going to the S2 state, then it has to come back to the S1 state, which is the S1 state is the lower singlet excited state. Always this fluorescence means coming back of the molecule to the ground state by relaxation process where it is emitting certain radiation, that is fluorescence. Always this fluorescence happens from the S1 state to the S0 state. It's always fluorescence happen from S1 state to S0 state. It's not from S2 to S3 like that. Always fluorescence takes place from lower singlet excited state to the lower ground state. This rule is known as Kasa's rule. Kash, Kasa's rule. Okay, so this is a very famous rule for the fluorescence spectrophotometry. Then sometimes what happen, now you are clear with absorption and fluorescence. Then sometimes what happen, if the molecule is in the S1 state or in the higher excited state also, it S1 and T1, all this maybe you are clear in inorganics while studying the inorganic part, singlet and triplet due to spin multiplicity, that I'm not going in detail, this singlet and triplet states. So sometimes what happen, the molecule moves from the S1 state to the T1 state through the process which is known as your intersystem crossing. Here one phenomena is there. We will not go into that because that is also not mentioned in your course. But however, you should know that that is a phenomenon which is known as spin orbit coupling. Okay, spin orbit coupling. Due to that spin orbit coupling, it moves from the S1 state to T1 state. Then, after moving to the T1 state, it comes down through the phosphorescence process to the ground state. So, the radiative process which is happening from T1 state to ground state S0 state is known as phosphorescence. So here from the all these things you might be clear that phosphorescence takes a long time since it is coming from the molecule is going from the S1 state to T1 state, which is according to the selection rule, it is forbidden transition. Always S to S, T to T is allowed, but S to T, T to S is not allowed. Not allowed transition. Like the way we are discussing the selection rule for IR, here also that is the thing. So always forbidden transition means it will have less intense. So phosphorescence are less intense as compared to your fluorescence spectrum intensity. So this is what is fluorescence and this is what is phosphorescence. Then we can move further. Okay. So what is happening one by one? If you see, activation is happening means it is going to the up state. The absorption of a molecule of suitable energy causes the molecule to get excited from the ground state to the excited state. That we understood. This phenomenon is known as excitation or activation, which is governed by Frank-Condon principle. So, what this principle says that this one quite often it comes in net gate. If you are preparing for net gate, then it is from spectroscopy like fluorescence emission spectroscopy, you might get this question. I was telling you one about Born Oppenheimer approximation. Once I was telling you that. Today I discussed the Casas rule. Then Frank-Condon principle normally comes, where what it is saying that electronic transitions takes place so fast. I was telling you, it takes place within femtosecond time scale, 10 power minus 15. Electronic transitions takes place so fast that the molecule doesn't get any time to change its internuclear distance. Now you imagine, here one question comes, which is not mentioned here, but quite often if you go for higher studies or some, you will face some interviews and net get oriented questions. Always you might have marked, we are just putting a straight arrow. We are just putting a straight arrow for the absorption or some processes. Why so? Why not tedha meda like that? Why you are doing that? Because when an electronic transition is happening, it happens very fast. It happens very fast, and this absorption thing 10 power minus 15, so the internuclear distance doesn't change for a molecule. Okay, so we designate as a straight line. So that is what is Frank-Condon principle. So after the activation, it is moving to the excited state. By showing the diagram itself, I was making you to understand. Then obviously after activation, deactivation process also will be there. So non-radiative deactivation and radiative deactivation, which I was discussing with you. So non-radiative deactivation is accompanied by some radiative loss also. Okay, sorry, are not accompanied by radiative loss because non-radiative. So how it happens? Through internal conversion, vibrational relaxation means just simply the heat dissipation. Through heat dissipation, it loses energy and comes to the lower state. Remember these two, internal conversion and intersystem crossing. Internal conversion is what? See, within S2S state or within T to T state, if some radiative, non-radiative transition is happening from the same spin multiplicity S1 to S2, S2 to S1, or your T1 to T2, like that, we say it to be internal conversion. If the non-radiative transition that is happening within the different spin multiplicity, that is S1 to T1, then we say it to be the intersystem crossing. So these two are the non-radiative transitions. I think you all are clear with that. Then radiative deactivation, we already discussed by showing the figure. However, we'll discuss completely thoroughly. So when the molecule in the excited state relaxes down to the lowest vibrational level, it may emit the photon and come back to the ground state. This process is known as fluorescence, which I have already told you by showing the figure. And it takes place in the time scale of nanosecond, 10 power minus 9 second. Mostly within the range, if you see, then it is 10 to power minus 9 to minus 6 second. Okay. And another radiative transition relaxation process that can arise from the excited molecule that had crossed over the triplet excited state by intersystem crossing process has the relaxed to the vibrational ground state in the triplet state, then such molecule will emit photon and comes down to the ground state S0 state, and this phenomenon is known as your phosphorescence. But phosphorescence, as I was telling you, triplet state to singlet state is theoretically forbidden. Okay, and it takes place so slowly that I was telling you, it takes place so slowly because of the forbidden transition and the movement of a molecule from S1 to T1 state. Then it takes place in the time scale range of 10 power minus 4 to 10 to power 2 second. Okay, since the fluorescence emission takes place, here you need to understand, here you see this figure. This blue one is excitation spectrum. This green one is the emission fluorescence spectrum, and the red one is the phosphorescence spectrum of a particular molecule, that is phenanthrene. So just see the wavelength wise, if you see, then emission processes are always occurring at the higher wavelength as compared to your excitation process. Okay, excitation process means it is observing and going to the up state, and emission processes are at, we are seeing at the longer wavelength. Why so? Because if, since fluorescence emission takes place only after the excited molecule has relaxed to the vibrational ground state is one state, then after having lost part of its energy, the energy of emitted radiation is lower than that of the excitation radiation. So energy, it is losing some, absorbing molecule is absorbing some energy, it is losing some energy in that way. Then when relaxation, it is of lower energy. This means that the wavelength of fluorescence emission could be greater than the excitation wavelength. So further, since the energy of triplet state is of the molecule is lower than that of the associated singlet state, you saw in the figure of Jablonski diagram, the transitions to the ground state are associated with emission of light still at the lower energy. So you get phosphorescence again at the longer wavelength. So as compared to your excitation, you are getting emission processes, that is fluorescence and phosphorescence, at the longer wavelength region. And if you compare fluorescence and phosphorescence, then phosphorescence comes in the more longer wavelength region. Okay. So coming to the fluorescence spectrum, which you want to see, spectrum already you saw for the phenanthrene, but here another example is also there, that is 9-methyl anthracene. This is excitation spectrum and emission spectrum. Here another concept is coming, that is Stokes shift. What is that? Now the wavelength difference between the absorption and fluorescence maxima. Suppose here you see, this is the maximum wavelength, maximum intensity for the excitation spectrum. You are seeing the blue line. Blue line is the excitation spectrum. In that maximum intensity you are getting corresponding to this peak. So here if you put a line, this line if you put here, then you are getting the wavelength here, that is 300 something. Okay, then if you see the emission process which is designated in the green line, the maximum intensity you are getting at the this wavelength 400 something. So the difference between this 400 something and 300 something, that difference whatever it is coming, that is known as your Stokes shift. Okay, so the wavelength difference between the absorption and fluorescence maximum is called Stokes shift. This concept also you should know. So, which kind of species will show the fluorescence or phosphorescence? We have already studied Raman, IR, UV visible. You saw, you got the concept of some spectroscopic tools are good for the molecules which are having dipole moment. Then you saw Raman spectroscopy is good enough for the molecule which are showing your polarizability. So, which type of molecule will show you the fluorescent and phosphorescent features of spectroscopy? Just a minute, water I am taking. Okay. So, what is happening here? That there is no specific requirement in a molecule that makes it fluorescent. There is no specific requirement. Remember this one. However, there are common observations. Means by certain observations only, we are designating that this kind of molecule may be fluorescent, that kind of molecule may be phosphorescent. But only by, if you will just tell me, madam, this is a structure of a molecule, organic molecule, can it be fluorescence? From the intuition or from the theoretical concept, I may suggest you that okay, it may be fluorescent, may not be fluorescent, but it need not to be my saying is right that it is fluorescent. No, but here you see the fluorescent molecule. Okay, the compounds with fused ring are mostly found to be fluorescent, and extent of this ring, if the extension of ring is more, then what will happen? Consequently, what will happen? It will be your conjugation is more, then it will be fluorescent. But if you see this one, phenolphthalein, phenolphthalein it is a rigid structure. If you see fluorescent, it is a rigid structure. The structural rigidity that favors fluorescence. Structural rigidity favors fluorescence. That also you can remember. If the extent of conjugation is more, then also the molecule can show you fluorescent. If you see these two structures, fluorescein and phenolphthalein, the structurally it looks almost same type, but phenolphthalein, you have observed during your experiments, phenolphthalein shows colorless to pink color, that things. That observation is different. You must know why the color change is there, but that color change is different due to pH variation, ring opening structure, all that things happen. Need not go to that part. But here you see in fluorescent, the conjugation is persisting. There is conjugation among the rings. But here for the phenolphthalein, due to this middle part, your conjugation, it is not a conjugated structure. Okay. So this kind of molecule will not show you fluorescent. These are non-fluorescent in nature. I'm just telling you all these things, but if you go through the contents of this material which is given to you, which has been uploaded in the IGNOU website, it is very good enough for spectroscopic method. I have not gone to the different subjects like your separation method is there, like your analytical other methods are there. I have not seen that materials, but as far as this is concerned, you are having many structures, many implications, many things are there. This is good enough for your study part. So here we can also see one thing here, biphenyl and your fluorine. Okay, these are of low quantum yield and they will give less intense thing. Wherever conjugation is missing, again you may not think that it will be fluorescent in nature. So the fluorescence observed with rigid cyclic molecules with pi bonds is found to be enhanced by the electron donating groups. If you remember your organic part, that there should be, if your pi bonds are there, conjugation will be more. If electron donating pushing groups are there, then also conjugation, it will be enhancing the conjugation, while the electron withdrawing groups will reduce it. Okay, that is also a criteria. If something is given, some molecule is given to you, it is fluorescent in nature. If you are putting or attaching or synthesizing another molecule by attaching a electron pushing group, electron donating group, then you may get more intense fluorescence out of that molecule. Okay, so, on the other hand, the non rigid molecules do not flourish much. I was telling you, rigidity of the molecule is also matters a lot. Okay, so that is one criteria, conjugation is one criteria. Conjugation is the main criteria. So, you need to see that. Here, another observation you can see is the simple heterocyclic compounds like pyridine, furan, thiopine, pyrrole do not flourish significantly. But when they fused with the benzene ring, they may become highly fluorescent. Just see the beauty of this fluorescence. Means switch on, switch off mechanism. If you conceptually try to understand this part, it is a on-off type mechanism. Pyridine by itself is not fluorescent, but if you are fusing if you are doing the fusion of pyridine with attaching a benzene ring, then it is fluorescent. Quinoline, it is becoming fluorescent. So this is the thing. The beauty of this kind of moiety is like this. Okay. For example, the heterocyclic pyridine is non-fluorescent, but quinoline, isoquinoline are fluorescent because of highly conjugated double bond. Conjugation is more, flowing of electron cloud is more. So that is why that is the thing. But another possibility is there when your molecule is not fluorescent. It is not fluorescence. If you like organic chemistry, if you are an organic synthesis person, then you can always try to attach a moiety or attach a group or attach something to it, chemically attached molecule, which is known as fluorescent tag or fluorescent label, which will try to enhance the fluorescence of the non-fluorescent molecule. That is also possible. Here I want to make you to understand why all these things we are doing. We are attaching molecules, synthesizing, making it fluorescent. Many drug molecules are there in the market. Many drug molecules are there in market which are fluorescent in nature. Okay, and many are there which are non-fluorescent in nature. But if you are taking a drug molecule or a compound which is fluorescent in nature, it is having its own advantage also. As far as you are studying the biological fluidic medium, You can take the fluorescence imaging of that. Last class I was telling you the neuron image. Neuron image, you saw neuron is so like thin, your knobs are going on. But if by using fluorescence spectrophotometry, you can study the structure of neuron. So that is so powerful. Main important thing with your fluorescence is it is very, very, very sensitive. It is very sensitive. And a little bit like a micromolar concentration of a substance is good enough for studying your fluorescence spectroscopy. Okay, that is the best beauty of this fluorescence spectroscopy. So now coming to the factors that affect fluorescence or phosphorescence, by using your conscience or using your thinking process also, logically you can find these process, these methods, how it will be affecting your fluorescence or phosphorescence. So if you are increasing the temperature, if you are increasing the temperature, almost always accompanied by the decrease in the fluorescence. Okay, change in temperature causes change in viscosity of the molecule, then collision among the molecule will be more. If collision is more with the among the molecules or along the solvent molecules, then some part of energy they are losing there. So, if you are going to see the fluorescence, obviously you will be getting less intense fluorescence out of a normal A or B. That is one. Here, another thing I want to show you, the molecule or the component which gives you fluorescent is known as fluorophore. That compound is known as fluorophore, or sometimes we also say it to be fluorescent molecule, fluorescent probe we say, which probe we probe the environment of the system. Then coming to pH, how it affects pH, how it will affect your fluorescent. Relatively small changes in pH can also cause substantial changes in the fluorescence intensity and the spectral characteristics of your fluorescence. One example is there, that is aniline shows fluorescence while it is in the acidic solution. It doesn't show fluorescence due to formation of anilinium ion. Okay, the most important thing is you saw from the structure part also. Sometimes it is fluorescent, sometimes it is not fluorescent. So whenever it will have conjugation, it will be fluorescent, otherwise it will not. So every molecule will not be pH sensitive. So don't, it is not a general thing that it is applicable to all the fluorescent molecules. So some molecules are very pH sensitive also. So coming to dissolved oxygen is having paramagnetic, it is a paramagnetic character substance. Okay, and many transition materials with unpaired electrons dramatically decreases the fluorescence as cause interference in the fluorimetric determination. So in elaborately it has been given here, but the thing is we must understand there are certain substances also which decreases your fluorescent nature. Then coming to the solvent, solvent plays a very, very important role in fluorescence spectrophotometry, studying measurement of the fluorescence spectrum. How? Now, if you are changing the polarity, the fluorescence spectrum, which I was showing you in the last figure, some figure I had shown you, then if you have taken that one in water, if you are taking that in hexane or cyclohexane, then the shift in that spectrum you may observe. The difference in the effect of solvent on fluorescence is attributed to the difference in their ability to stabilize the ground and excited states of your fluorescent molecules. Okay, so the solvent effect, it is a solvent effect itself, like while studying the fluorescence, we take normally 2 to 3 classes to make someone understand the solvent effect. Because what is happening, just I am giving you a glimpse of idea about it. If you are taking a molecule in a solvent medium, you are exciting that molecule. Don't you think you are also that solvent molecules which are associated with that molecule, that also will absorb certain energies? Then polarization around that thing will happen. That fluorescent molecule, solvent around the fluorescent molecule, will stabilize that molecule to some extent. Means energy wise, it will come from the emission, will come from the lower excited state. So, if you are increasing the polarity of a solvent, your this thing, your spectrum, you'll be getting at more and more longer wavelength, more longer wavelength. If you are taking in hexane and water, then in water you may get the spectrum at the longer wavelength as compared to in hexane. So now come to a concept, that is your fluorescence quenching. This is a very important thing, fluorescence quenching. Quench means from the word itself, you may be clear. Quench means to suppress, to reduce, to retard the thing. So fluorescence quenching means some way there is decrease in the intensity of the molecule which is fluorescent in nature. So this decrease in the fluorescent intensity arising out of the interaction of the excited state of fluorophore with its surrounding is called quenching. Okay, so one of the mechanism of quenching involves collision between the excited and ground state molecule, leading to increase in amount of your radiation less relaxation, which is known as self quenching. I'll just make you clear here. What it is saying, that there is collision between the excited state and ground state molecule, leading to increase in the amount of radiation less relaxation. So radiation relaxation amount will decrease. Okay. Cell quenching means that molecule is becoming a quencher of that itself. Quencher money. What is that quencher means? That quenching means retardation. Quencher means which is responsible for the fluorescence quenching. Okay. Now you need to understand what is happening. Collision between excited state and ground state of that same molecule. If 100 molecules are there, 100 molecules are there around that, don't imagine that 100 molecules means 100 molecules are simply sitting with cool mind. No, it's not that. You are making a solution of that. Around that solution case is there, solvent case is there. Around that many things, different processes are also involving with that. It's not that simple. If 100 molecules are there in a solvent, it need not to be 100 will go up by observing the energy. No. Sometimes some molecule will be in the ground state, some will be in the excited state. Random thing, random. But it is a relative thing. As I was telling you, the Boltzmann distribution, the population distribution. Population of what? Population of these molecules, that is indirectly we say concentrations, are very, very important. But some will be in the excited state, some will be the ground state. They will have collision in between. Due to collision, obviously, they will release energy among themselves. So, if they are releasing energy among themselves, means someone is dissipating, someone is accepting, then what will happen? While coming to the ground state, obviously, it will have less energy to emit. So less energy to emit means less wavelength that scanning you will be doing, it will come of lower intense peak. So that is what is your self quenching. Okay. If sometimes what happen, there's self quenching, need not to have self quenching. Here one quencher is also there. Means additionally you are adding some quencher. I'll show you many examples by adding some external quencher. You can also study the quenching process. When the molecule in the excited state coming in contact of the quencher, it is just relaxing back as M, and the relationship which the quenching mechanism completely we can discuss is your Stern-Balmer equation. This Kf0 and Kf are your fluorescence quantum field for the analyte or the fluorophore in absence and presence of quencher. And Ksp is the quenching constant. See, you are seeing these things, you are studying theoretically, but how you can apply that things? It is really, I was telling you, while now you just get a concept of all these things, but further you may study more and more if you want to study, go further in that process or in that field of research or anything. I will show you one two papers where we have also used these quenching processes, so that you will see, okay, not only I am studying theoretically, it is then having application in the subsequent parts. So we'll discuss that if time permits. If time permits, I will definitely show you one to research papers where we are for using this kind of things also. So come to quantum field. Quantum field, if to a layman, if you say what is quantum field, who doesn't know anything about quantum field, then in a way you can project in this way that if a molecule is having more quantum field, then it will show you more intense fluorescence peak. If a molecule is having less quantum field, then it will show you a less intense fluorescence peak. So quantum field is directly related to your intensity factor, which is your it is defined as the ratio of number of emitted photon divided by number of observed photon. So number of emitted photon will be more, means obviously your quantum field will be more. Obviously your intensity, fluorescence intensity will be more. So this is your quantum efficiency or your quantum yield we say. So how efficient a molecule is from you can predict from its quantum yield. Different molecules, 100 type of molecules will be there, which is good to which is fluorescent good, fluorescence not good. From the quantum efficiency, you can predict its efficiency towards your fluorescence intensity. This is also designated by lifetime factor also, that is quantum yield is equal to tau by tau 0. This tau is tau and tau 0 are fluorescence lifetimes in presence and absence of non-negative processes. Actually, if I go to the lifetime part, again it takes more time, but uh, it's not that I am not going because of that, but it's not there in your course. In your course, it is not mentioned in the subsequent part also. But to have a knowledge on lifetime, let me tell you, put you in this way, that the molecule is going to the excited state, and how much time it is staying in the excited state, we say it to be the fluorescence lifetime, but not exactly that. It gives you feeling of that, but exponential molecule comes to the ground state, exponential decay of a molecule happen, exponential decay. Okay, So half of the path when it covers, that is your one eighth of the path it covers, that is your fluorescence lifetime. Okay, so that is not there in your part, so that is why I'm just skipping that. I'm not skipping, I'm not telling you in the detail of that, but I will show you one two research papers, I will show you, so that you will have a understanding of this. Whatever you are studying, it is also having applications. So, instrumentation for fluorescence measurement, like the way you saw everywhere, there is light source, there is a sample holder, then your monochromator, then your detector, and then your output device will be there. But here, some way we need to make us clear that if you see for the absorption spectroscopy, UV visible spectroscopy, this was the design. What was there? Light source was there, sample was there, detector was there, parallel in that direction itself. Okay, but here light source and your sample holder is there, detector is there 90-degree angle. At the 90-degree angle, it is there. Okay, why so? Here the answer is mentioned over here. All fluorescence instruments are essentially the same component as are used in the absorption spectrophotometer. Same components are there. Components are same. Like sample holder is there, detector, then output device, component is there. However, the geometric arrangement of the components is somewhat different. The geometric arrangement is different. This is due to the reason that any transmitted radiation is not measured along with fluorescence. Any radiation that is transmitted, we are not measuring in the fluorescence. Okay, so you know that the absorption and transmission of radiation energy occurs only along the direction of the incident light. Along that direction it occurs. How, whereas the fluorescence radiation emits in all directions. So fluorescence normally comes in all directions. In order to avoid that other parts, it is always better to put the detector in the 90-degree position. The detection of the transmitted radiation is avoided by placing the detector at the right angle. So this is the basic difference what we are just going in doing in absorption spectrophotometric method and here for the fluorescence. But otherwise, all components are almost same. That is, excitation source is there, then a monochromator filters will be there, which will tune the radiation. Then sample holder is there. Then detector will be there. Then reading put output device will be there. Sample holder, I had shown you already in the last to last class that sample cuvette, quartz cuvette I was showing you. Also solid sample cuvette holder are also there. So this is a complete layout of the fluorimeter. Okay. So here you are having a light source, then a monochromator which will select the wavelength, the proper wavelength radiation. Then it is falling on the sample compartment. Then, as we are discussing, there is the radiation will be emitting from all directions. So, in order to avoid the transmitted radiation, we are not putting the detector in this side. We are putting the monochromator here. Again, it will filter, it will cut the other radiations also. It will make the single wavelength radiation, monochromatic radiation will get here. Then it is going to get scanned through the detector where photomultiplier tubes will be there. It will amplify the signal. Then you will get the output. Output, how you are getting? The spectrum I was showing you. The spectrum you will get. Okay. So source, what source we are using here? The source here is very, very important. The absorption spectroscopy, if you remember UV visible spectroscopy, I was telling you, it is a ratiometric technique, right? Log I0 by I is equal to epsilon C. I was telling you I0 by I. Ratiometric technique. If your source, you are increasing the power of source, then is it going to happen? Is it going to make any change in the absorption spectroscopy? Not much, because it is ratiometric, I0 by I. If you are increasing the power also, ratiometric technique wise, it is not going to make any more changes. But here, the fluorescence power or intensity is directly proportional to the source power, directly proportional to the source power. So therefore, the source must be a good intense than as compared to you required for the UV visible spectroscopy. And here, basically, Xenon arc lamp is used as the source for the fluorescence spectrophotometry study. Okay. Then wavelength selector is there. Wavelength selector means your filter will be there. Then monochromator will be there, which will cut some other radiations, other wavelength radiations, and a monochromator. If you will put, then your monochromatic radiation means a single wavelength radiation you will be getting. Just let me show you the example. See, this one I was telling you, this is physitin. Physitin is a fluorescent molecule, as well as it is a strong fluorescent molecule, as well as it is a bioflavonoid. It is an antioxidant. So the beauty of this molecule is it is fluorescent in nature, and if you are taking it in liposome membrane, liposome all of you know that if you go and see you applying cosmetics, you are just taking the cosmetics and applying. But have you seen the composition? You will be seeing lauryl sulfate or any kind of surfactant will be there, which will make you that glossy type thing, and it will release that components involved in the cream in a slow drug release way. Okay, slow release way. So this liposome membranes, bilayer membranes you have already studied. So just in laboratory itself, you can study the uh, different through fluorescence different interaction. If you see this molecule is showing different spectrum, one black is there in water and different spectrum in lipid bilayer membrane, the green one. So just imagine a single molecule is so sensitive to the your to the environment. It is so sensitive to the environment. So it is staying in the inside the bilayer membrane or outside the bilayer membrane. You can also study these things through the spectroscopic tools. If you see, I was telling you about the quenching part. See, temperature. Temperature effect also, you can see if it is of lower temperature, its intensity is more. If you are increasing the temperature, its intensity is going down. Temperature effect is also there for certain molecules. All molecules will not be pH sensitive also. Okay. Then, if you see the quenching part I was telling you, see microscopic image. Just you put in a solution or biofluid, biosamples, These molecules which are sensitive to stick to the liposome membranes or micellar systems, they will stick there. Then they will flourish. So other parts, other black regions you are seeing, just simply water. Wherever your membrane is there, it is just attaching to that membrane and showing you a glowing part. Okay, so these things you can study very well. The quenching, I was telling you, quenching that KSB, normal quenching or constant and all that things you can also study. Here you see, this is a quencher, CPC is a quencher. When you are adding to the solution, its intensity is going down. Its intensity is going down. So quenching these normal theories, whatever you are studying now, you can apply it for research purpose also. You can apply it for research purpose also. You can study these molecules through fluorescent spectroscopy. You can do it very well. Okay. So these are having the importance. These studies are having importance. Since we are running behind. I'm just giving you the idea of that. Then only your interest will come. Like to study chemistry, and chemistry is a very good subject actually. So sampling, coming to the sampling, I was showing you in the last class, their cuvette was there, the quartz cuvette, as well as I am also having the solid state sample holder also, where you can press you can keep the powder sample and just squeeze the sample, the screw it, then you can keep it in the fluorimeter, then you can measure it. I could have shown you the fluorimeter today. Mm, then it would have been better. Anyway, time. Let's see if time permits. Then I will show you the fluorimeter. So there is detector which is almost inside the fluorimeter. So it is having the photomultiplier tube. Okay, so it is amplifying the signal. Then you are getting in the signal in the readout devices, and that is the simple thing. No problem. So phosphorescence also, there is a sampling technique for the phosphorescence, but phosphorescence mostly we need to study at low temperature. So at the low temperature, so that you will get a very good signal. So quenching will be minimal inside that. Then the sample tubes are placed in a liquid nitrogen held in a quartz Dewar flask, which is then placed in a sample holder, okay, called phosphoroscope. So this is the sample holder, sample tube. You are just putting that sample tube. Then recording procedure is almost same. That excitation radiation you are just putting into the sample holder. Then emission monochromator will be there, and you will be studying the emission. Then coming to the application part, actually the application of these portions are very, very, very vast. Nowadays, in laboratory, in forensic science, in your biomedical engineering technologies, biotechnologies, everywhere, life science, everyone using this fluorescence because it is having a amazing good technique and less concentration of molecule you can use to get its sensitivity is very, very high for this technique. Okay, so the fluorescence spectroscopy and its application to physical and life sciences have evolved rapidly during the past decades. It is widely used in the qualitative and quantitative analysis. Okay, both you can use for the qualitative as well as quantitative analysis. If you imagine yourself till now, whatever you have studied, that quantitative analysis means your molecule means concentration related, right? So if your molecule you are getting good intense fluorescence, then you can say it is having the population is more or concentration is more. Then by plotting a reference sample or calibration plot, you can predict also the concentration of a unknown sample too. Here you see some common applications. Day to day life, you will be just seeing vitamin A, morphine, then alicharin. These all are like drug molecules, in some way drug molecules, and vitamins. They all are fluorescent in nature. They are fluorescent in nature. And the example of application, that foodstuffs, vitamin tablets, body fluids, drug preparation, environmental samples, water sampling technique, soil, everywhere you'll be seeing the fluorescent. Just now also, if you think in the road night time, some glowing stickers will be there. What are these stickers? What is the nature of that stickers? That will have fluorescent or phosphorescent properties. Then only they are showing the glowing nature, as well as some dye molecules which are fluorescent in nature. You are also putting in the flight. You have seen flight wings. In that wings, you put a dye of your fluorescent nature molecule. It will be glowing, so that you can see, okay, something is moving there. Okay, so these are fluorescent in nature, and you are having a vast application of these fluorescent molecules as well as phosphorescent molecules. Okay, we come to the summary part. Good. So this is what is your fluorescence and phosphorescence. Okay, so let me go to the next module. That is the same thing. That is same next module is your fluorescence only. The next module is analysis methods. Okay, application of fluorimetry and phosphorimetry. Analysis methods are there. So we can see that. Just if you give me one second, then I'll just make you, I'll just ready my fluorimeter to show you. Just 1 second. Switch on that instrument. So in between, within 1 2 minute, that instrument part will be ready, so that I can show you the instrumentation part. Am I audible or disconnected?
Yes, ma'am. Audible.
Okay, fine. You just switch on that instrument. They should see the general lamp glowing also, and any spectrum we are having, so that we can show. So versus any spectrum is there, we can show. Just I want to show them how we are taking and how the general lamp glowing is there. This is the cuvette. Cuvette, just take it. So versus take this cuvette. Okay. In a minute I will show you. So let's come to the other unit. We need to finish this also. So fluorescence analysis methods. You can do direct analysis as well as indirect analysis. What is that? Direct analysis, you are just taking the molecule which is fluorescent in nature. Like here, I'll give you one very good example. The proteins which are bodily available, that is having tryptophan and tyrosine. This tryptophan and tyrosine by itself they are fluorescent. So I don't need any other molecule to take in the solution and take the fluorescence of that. I don't need that. Okay, so that is the direct analysis method. We measure the natural fluorescence of the analyte which we are going to study. But indirect analysis, what happens? Some solution I want to study. Liposome solution, micellar solution, biofluid, where there is no fluorescent, that fluid is not fluorescent. Then how I'll study through fluorescence? But I want to study through fluorescence. Then what I can do? I can add some other molecule to it, other fluorescent molecule to it to study. I was showing you that example, this paper I was showing you. Here, the system is liposome membrane. Membrane is not fluorescent. But in order to study this property of this membrane, property of the membrane, fluidity of the membrane, what we have taken? We have taken visitin as the fluorescent probe, or you say fluorophore. Okay, so this is an indirect way of studying the bilayer membrane. So that is what I want to make it clear what is the direct analysis and indirect analysis. Okay. So it is basically used for the quantitative analysis, hmm, as well as qualitative analysis also. Quantitative analysis, mostly I told you that concentration dependence fluorescence. Concentration dependent. In the UV visible part also we studied. It is concentration dependent studies related to your quantitative part. A spectrometer method can be put to quantitative analytical application only if the spectral characteristic like position, intensity, width of the spectral band can be related to the concentration. This is the simple concept you need to understand. When I can measure there is change in concentration or change in something quantitatively, if there is some change means if there is the UV visible spectrum you are seeing or fluorescent spectrum you are seeing, if the spectrum intensity or the spectrum position means towards the longer wavelength or towards the lower wavelength, if it is changing that, okay, or width of the spectral band, if the width is narrow, width is increasing. So any changes if you are seeing in the spectrum, then only you can analyze the concentration of the analyte. So for different technique, you are going to use in different ways. Okay, the UV visible or fluorescence or anything. So here, through quantum field measurements, you can predict the samples or concentration of analytes. So this intensity is proportional to concentration. Thus, the fluorescence intensity of sample can be used for the concentration determination of the analyte. Okay. Factors affecting this quantitative analysis. Last unit, whatever we have studied, the same thing, the same like concepts here we are using. Both the units are interlinked. Okay, factors that affect the quantitative application in fluorimetry. Self quenching, that will affect the quantitative analysis. How? As I told you, the same thing you should remember. If my intensity is changing, or my spectral width is changing, or the what to say position is changing, then only I can predict. So, how the factor will affect, what factors will affect the quantitative application? The factors which are responsible to change, to bring a change in intensity or in position or in spectral bandwidth that will affect the quantitative application in the fluorimetry. Is that clear? So self-quenching will affect the quantitative analysis. Okay. Last class I was talking you about the inner filter effect in the UV visible spectrophotometry. Sometimes what happens if you are taking more concentration, you'll be thinking, okay, I will increase the concentration too high that my intensity will be very good. No, there is limit to everything. When you are deriving any theory, you are putting many assumptions to it to derive it. Similarly, there are certain limitations to everything. If you are increasing the concentration too high also, you will be not getting. You'll be not getting your fluorescence a good way, because the solution, whatever you are taking, in between that, what will happen? In between that, your they themselves will act as the filter in front of the radiation. They will act as the filter. So that is what is your self quenching. Then radiant energy of absorption. Absorption energy is also important. How much radiation is getting absorbed by the analyte, how efficiently that analyte is able to absorb. Otherwise, it will, if there is less absorption, then emission also will be less. It's on. Start here. No, no, just open it. Open it. I want to show them. Just a minute. I'm going to show you the spectrum. Okay. So see, this is your fluorescence instrument. Here you can see, if I am taking it like this is sample compartment. Are you able to see here?
No, ma'am, it's very small to see.
Or
There is just
can you put your torchlight here? Mobile touch. This sample compartment is there. See, here one sample compartment is there. Okay, this is the sample compartment. Huh? Here one cuvette is there. I am taking this cuvette. Okay, this cuvette, you have to put the solution in this cuvette and keep in this sample compartment. Okay, you have to keep in this sample compartment. Here this side radiation will come, and this side 90-degree the radiation will go, and here monochromator compartment and optical things are there inside this. Okay, so this is what is the basic arrangement which we are able to see. We will be able to see only the sample compartment, but inside that part where the light source is there, Genel lamp, or this side where the monochromator is there, that is optically designed, that we cannot see. But here we can see the sample compartment. We'll put the sample, then the output device. See, here you can see this green lights, you'll be seeing this lights. This is the Genel lamp indication that it is on. Genel lamp. Okay, the lamp is also on inside. Here the monitoring unit is there, where you can see the spectrum. In a spectrum you can see, you can get the spectrum. This is a Rayleigh line for water we have taken. This is the this is the Rommel line we are seeing. Then another some impurity is there in that water. That is why this hump is coming. This is one spectrum. So various here, if you see carefully, then various other parameters are there to see whether the like software design things are there. Okay, software design things are there. So you can just any good spectrum is there. We can show them any good spectrum apart from water. Okay, here you can see this is one spectrum. The peak intensity is here. Here one hump is there. So basically what we do, basically what we do that we take a sample, we keep in there. Okay, if you want to study some biological sample or anything, we keep there, then we just go for the measurement. Then after getting the measurement done, we analyze it. We analyze it by seeing various research articles and various things. Then we go for the analysis of that part. Then we come to a conclusion. Okay, we come to a conclusion about that. Okay, then let me move to the part. Okay, so this we can close. He was my PhD student. Thank you, Sivasis. Okay. So self-absorption, another mechanism causing the deviation from the linear dependence on concentration at high concentration of analyte. I was talking about the high concentration of analyte. High concentration, if you are increasing the concentration, then the radiation which is passing through, the emission radiation which is passing through, again it will encounter with the other molecules nearby. Understood? So emission that is coming out of that solution is not freely moving, because if you are increasing the concentration of the analyte more. Can you just give me that mouse? Now, if you are increasing the concentration of analyte, then your self-absorption, high concentration of analyte, self-absorption happens, which also can lead to the quenching of a solution. Then interfering species means any additional species that is getting, you are adding to the solution, like quenchers, like some impurities also may be there. So that are known as your interfering species. Okay, which also leads to your decrease in the fluorescence intensity, quenching of the fluorescence intensity. So quantitative, so it will definitely affect your quantitative analysis. For that, sure that it is going to affect. Then fluorimetric environmental monitoring. See, in simple way, if I will just try to explain you that some gaseous molecules are also there, which are also fluorescent in nature or luminescent in nature. In this way, if we'll put, it will be better. Are luminescent in nature. It may have fluorescence, may have phosphorescence, depending on the nature of the molecule. That if you will ask me, ma'am, how will predict if it is fluorescent or phosphorescent? We can't say it clearly by through words. We have to do the experiment in order to find out whether it is from giving you fluorescent or whether it is giving you phosphorescence, or you need to do a thorough study of the literatures. Whichever research is going on, based on that also you can say. So environmental monitoring also you can do by using this fluorescence, that is analysis of gaseous pollutants, the the analysis of gaseous pollutants is based on the phenomena of chemiluminescence. So chemiluminescence is a very good way of monitoring these gaseous pollutants. So determination of this NO, NO2, these are also you can study through fluorescence. If you see NO in the atmospheric ozone reaction, it is forming NO2 star. NO2 star means it is energized species. It is the energized species. Star designates energized species. But when it is coming, it is relaxing and coming to the ground state after the excitation. Okay, it is releasing certain amount of photon. It is releasing some radiation. It need not to be always whichever molecule is absorbing certain radiation and getting excited. It need not to be always true that it will emit some radiation. No, there may be heat dissipation also. That is why we are saying some molecules are luminescent in nature, some molecules are fluorescent in nature, not all. So this here NO2, you can predict in pollution, in air contamination, you can predict NO2 like in this way. Okay, you can predict NO, how much, you know, by passing through the reactor in which it reacts with the ozone. Initially, it goes to the NO2 excited species, then it relaxes back by emitting certain radiation through chemiluminescence process. Then you can study it. Okay. So this is what is the mechanism. So everywhere you will have your sample compartment. Sample compartment you have to design of your own way. Like if you want to study solution phase, I mostly study in solution phase. So my solution sample holder was there, but I also have the solid phase holder where I can show you the solid phase compartment how it looks like. If you are dealing with the gaseous chamber part, then you have to put the chamber combustion chamber in such a way that there will be certain reaction is going on. Then obviously light is you have to put the light on it. Then the simple method is there will be detector and a output device. Okay, so everywhere the technique is same. Technique is same. So determination of SO2, also that sulfur dioxide also you can predict through the fluorescence chemiluminescence method, that also you can predict. So you can imagine that in whatever way you can use these fluorescence techniques, very elaborately this luminescence you can use. So in the fluorimetric method, how you will use this SO2, so sulfur dioxide, how you will measure that a pulsed UV source is employed to excite the SO2 molecules. These excited molecules emit a characteristic fluorescence with intensity that is proportional to concentration of SO2. Understood? Now the thing is quantitatively, if you want to measure something, then the pulse is getting applied on it, you are exciting the molecule, then the excited molecule is emitting certain characteristics fluorescence with intensity is proportional to concentration. That I was telling you, intensity is proportional to your concentration. Then accordingly, you can tune the things. If you are having a calibrated plot already with a particular reference whose things you know, then you can get the concentration of the unknown analyte which you are going to study. Okay. So there are various methods to study, but the fluorescence method I was telling you that. Water pollutant also you can measure through your fluorescence. Okay. As the concentration of aluminum in the water sample uh, may be very, very small, So you need to use a method which is very sensitive enough for studying that. So fluorescence is the best way to indicate any contamination that is available in water. So analysis of aluminum, as the concentration of aluminum in water sample may be very small, we therefore need a sensitive method for the analysis, and fluorescence measurement provide for such a method. Okay, for studying the aluminum analysis for doing the water pollutant analysis from water. The way I was telling you that some molecules are fluorescent in nature, some are not. If some moieties are not fluorescent in nature, but you want to study its property, suppose some analyte is not fluorescent in nature, then what will do? You have to think of a molecule, you have to think of a fluorophore which can bind to this analyte very well. If that can bind to the analyte very well, then indirect analysis method, you can predict how much that A compound is available in water. So that is the another way of predicting how much contamination or how much analyte is present in your sample. Analysis of fluoride in water, that also you can do. Fluoride content you can predict through the fluorescence also. For that you have to add certain analysis, some fluorescent tagging you have to do. The one I was telling you in the previous unit, fluorescence tagging is needed for that. So the fluorescence spectroscopy in medicine and biology, I was keep on telling you about the neuron example, or now I told you about liposome membrane, bilayer membranes, which are bodily available also. We have also studied the lipid bilayer membrane interaction with the bile, that pitta, bile substances we have studied that are also biologically having biological importance. So this use of fluorimetry in the field of medicine and biological samples is well established. I forgot in which year they got Nobel Prize, but for the jellyfish, greenish GFP, green fluorescent protein, for the green fluorescent protein, they got a Nobel Prize. It may be in 2011, I guess 11 or 12. Uh, Scientists got Nobel Prize. I forgot their name. So the use of fluorimetry in the field of medicine and biological samples is well established. In fact, the fluorescence technique has got a big boost with its application in biological sciences. So today, highly selective and sensitive. I am repeating it again and again because selectivity and sensitivity are two important. What? Close it. I am these are very selective and sensitive for the biomedical determinations, and it can be accomplished by fluorimetry. So spectrophlorimeter in the first class, people are having like they were asking about metry, all that things. By this time, we are seeing it again and again. It's not like we are not saying fluorimetry. We are also saying fluorimetry. It is more sensitive and selective than any usual spectrophotometry, like UV visible spectrophotometry. And this spectrophlorimeter is tailored to suit the need of your specific sample to be analyzed are available in the market. So you can do any kind of an analysis by using fluorimetry, but provided that molecule has to be fluorescent in nature, or provided that sample or that analyte which you are going to study, that is good enough to attach with a fluorescent molecule and can be studied further. Any clinical samples also you can see. From my experience, I am just telling you one thing. in forensic departments also we use this fluorescence tool as a to study or to probing some things. When I was in IIT Madras, that time one collaboration work has come where some butyl model was there, and application of surf on the body has been done. So they extracted the fluid of the body and they came to us for the fluorescent measurements. Okay, it has been observed that while doing that part of work, I'm not going to that analysis part, but we can do it by using fluorescence. While doing that, it came to my mind the curiosity. If you are checking different soaps like Surf Excel, Tide, or anything, that also you can study through fluorescence whether they are good enough or their oxygen quenching is more or less. That also you can study through fluorescence. But up to that time, I didn't have idea about that. But just subsequently, I found that it is this fluorescence can also be applied in that field also. So it is having very beauty of this fluorescence spectroscopy. Then analysis of amino acids and proteins. Proteins are, I was telling you, as such our body proteins are having tryptophan and tyrosine moieties, which are fluorescent in nature. By themselves it is fluorescent in nature, and amino acids, some are fluorescent in nature and some are not. So you have to use some extra fluorophore molecule to the system to study the fluorescence. Okay, so this is the thing. Then fluorimetric determination of blood glucose also can be done. That is, the concentration of the glucose is related to intensity of color produced. It is directly proportional to that. So nowadays, the blood glucose level are measured by the procedure based upon the enzyme named glucose oxidase. Since an enzyme is used, it is specific for only D-glucose studies and will not be subject to interference from other molecules in the blood. So specifically, that is going to bind with the D-glucose, and you are going to get the glucose unit or glucose related concentration peaks only. Any other molecules that is available in the blood sample is not going to affect that. This is a very important point also. If you want to study a body fluidic thing or anything, it will have so many other complex molecules also. You don't want them to interfere in your study. So you want a specific moiety or specific fluorophore which will attach or which will attack your sample of study or your analyte which you want to study. Then only you can go for this kind of fluorescence studies. Otherwise, it is very difficult to do analysis part. Theoretically, if you are reading, it's fine. But for doing the analysis part, it is very difficult if you are not using specific molecules. So, specificity and selectivity are two important factors which you need to understand. Okay. Then the analysis of blood serum also can be done. Analysis of calcium ion. Then some fluorescent characteristics of organic molecules of biomedical origin that are of biomedical origin. So this brucine or fluorine, then morphine, penicillin, nicotinamide, folic acid, these all are fluorescent in nature. Okay, and how sensitive they are? Among them, few are good sensitivity, few are having poor sensitivity. As I was telling you, sensitivity is very important thing. You need to select a suitable molecule for suitable study. But as of now, you should understand that these are of biochemical origins that is penicillin, folic acid, ascorbic acid. These are also fluorescent in nature. It is having certain wavelength of excitation and emission. It is having certain colors, and some are fair enough for fluorescent study. Some are not fair enough. Some are poor also. Poor fluorescent is also there. We were discussing about the chemiluminescence. Chemiluminescence, some luminescent property, the molecular swing due to chemical reaction. But there is existence of bioluminescence too. There is existence of bioluminescence too. So bioluminescence, if you remember, there is an insect which is your firefly. Night it will be glowing and moving all around, and the glowing greenish glow, that is because of luciferase enzyme. That is because of the luciferase enzyme that firefly is secreting from its body, for which you see green fluorescent glowing part. Okay, so that is a best example of your bioluminescence. So nature is also accepting this fluorescence technique very well, it seems. So the phenomenon of luminescence occurring in the living systems or the compounds extracted from the living systems is called your bioluminescence. So you might have seen a firefly may also could have come across the flashing fish, the jellyfish, the green fluorescent jellyfish that are also fluorescent in nature. You might have few people might have done the scuba diving or inside sea. You will find very luminescent glowing objects. Various fishes are there which are glowing in nature, and various minerals are there which are generally glowing in nature. The glowing parts we are able to see in our eye when the environment is dark, and that particular moiety is glowing. So underneath of the sea, you will find many glowing objects. That is due to your bioluminescence property of that fishes. Bioluminescence means they are secreting some enzymes from their body, secretion is there. So it is glowing in nature. And some minerals are there which are glowing in nature due to your chemiluminescence properties. So mostly your luminescent molecules are generally also it is available. Okay, some glowing glow worms are also there. Some worms that are also glowing in nature. Okay, some natural purpose of the glows are also there. So this is fluorescent and mineral analysis. Okay, this is fluorescent and mineral analysis. So several minerals like your calcite, fluoride, rubies, zircon, on exposure to UV radiation, they start emitting fluorescent. The only requirement being that substance inhibiting or quenching fluorescent must be absent. There must not be any inhibiting or quenching of the fluorescence. Otherwise, they will just as of their nature, they are fluorescent. Gypsum is one of the common mineral in the sediment environment exhibit fluorescent on exposure of UV radiation. There should be exposure of the radiation also. Some are good enough with the limited light, some are require more light also. Okay, so this fluorspar, the mineral form of the calcium fluoride, that is also fluorescent in nature. So there are various example of fluorescent minerals too. Okay, so these are some application of crystallospores of analysis of metal ions. There are various examples which are fluorescent in nature. Then complexing ligands for determination of metal ions, like uh, see, I was telling you, some metal ions are not fluorescent of their own. They are not fluorescent of their own. So what you have to do? You have to put a complexing ligand to it. You have to put a complexing ligand to it, which will attach to that what that metal which you want to analyze, and you can detect up to a certain limit how much amount of analyte is present. You can detect it through complexation by complexing that ligand with the moieties which are fluorescent in nature. Okay, then you can predict the samples, whatever amount it is available. So we have come to an end summary part. So I think all of you are mostly clear with this. Okay, any question?
Ma'am, in all the absorption spectroscopy, we use the monochromators before the sample holder, but in IR spectrophotometer, uh, we had a monochromator after the sample holder. Why this?
Sorry?
Ma'am, in all other absorption spectroscopic methods, we have
Hmm.
chromator before the sample holder.
Hmm.
But in IR spectrophotometry, we have the monochromator after the sample holder.
Dipti
Why?
Ranjan, you have
Yes,
you were there in my last class.
yes, ma'am.
I had already explained that thing. I had already marked that portions also.
Ma'am, I was there, but I only heard that thing that monochromator is after the sample. But
No, while explaining that, it is clearly mentioned there itself. It's clearly mentioned there that you want a good signal to noise ratio, and you want a good intense thing. However, your IR radiation is not that intense or not that powerful, not that energy wise strong. You are giving all wavelengths into the sample. You are not making it to be monochromatic. You are not putting a single wavelength radiation to the sample. You are putting all wavelength radiation to the sample so that it can absorb the radiations and go up. Then, while studying the emitted part, we are just putting the monochromator so that we can collect a signal. We can collect whatever radiation we want to study.
ma'am, all the
Okay.
radiation
And
all the
near to that question, one paragraph was written on that. Okay. Hmm.
ma'am,
Any question from fluorescence?
uh, fluorescence, ma'am, is there any inorganic material like strontium aluminate
It
which
is not audible. Tell me.
fluorescence? Ma'am, is there any inorganic material like strontium aluminate which phosphors for some time after the light is cut off?
Many inorganic molecules are there.
We have a large vast number of organic molecule which shows fluorescence as well as phosphorescence, but
Hmm.
in terms of inorganic matters, we have
Inorganic are various inorganic moieties are there. These metals are also there, which you can bind with the complexing ligand and study. Various inorganic moieties you can study. These gaseous pollutants we are talking about. In water pollutant, many metals are present. That also can be studied.
like oxygen, ma'am. Like oxygen,
Huh?
8
Like
hydroxy.
oxygen,
Yes, we can attach a nickel to it. We can detect nickel using oxygen.
that also can be done. like the way here copper is there. You can attach etiopropin, then you can study. Zinc also you can study. So you have to see the fundamental thing is which metal or which inorganic moiety you want to study. Accordingly, you have to predict with what you want to bind that moiety, with what you want complex in ligands to be. You can't bind this benzoyl acetone with every metals you want to study. There should be specificity and selectivity to the moieties both are combining and joining together. So that is the most fundamental thing we need to know.
And ma'am, how can we differentiate between a fluorescent molecule and a chromophore? Both have a conjugated system. So how can we differentiate between a fluorescent molecule and a chromophore?
Chromophore.
Chromophore, ma'am.
Just tell me what do you mean by chromophore?
It is a color enhancing moiety
Color
that
enhancing moiety or color enhancing moiety or color enhancing functional group or a complete molecule.
ma'am, mostly we have seen any chromophoric group that have a
Hmm?
conjugating system actually.
Exactly. You are
And
talking about homophoric
so
group that yes, see, Dityaranjan, you need to be clear here. You are asking me the question which is different thing. The fluorescent molecule, as such, you are talking about a molecule which is a conjugated molecule. Okay.
yes,
Now you
ma'am.
are asking me that is the chromophore and fluorescent molecule how to differentiate. Why you need to differentiate? Because chromophore it is a chromophoric group. It is a functional group which we are attaching to a molecule for the extension of the conjugation and to have a better absorption. Okay. So that
Ma'am,
is.
the
Hmm.
but they can means I am confusing. I get confused somewhere in the conjugation in both the scenario. In chromophore, we also have extended conjugation, and in
Chromophore not have extended conjugation. The
they in
chromophore functional group which is attached to a molecule.
yes, ma'am. They
Yes,
extend conjugation in the
ex-
molecule,
molecule.
but
That molecule can be fluorescent also.
yes, ma'am. I was confusing in that aspect actually.
That can be fluorescent also. But it is not always it will be fluorescent. All the absorbing species, all the dye molecules which are colored in nature may or may not emit radiation. May or may not emit radiation. In today's class, while beginning with the fluorescence, I was explaining that there is no specific scenario or specifically we can say this molecule is fluorescent or not. Yes, if it is having a conjugation, if it is having a chromophoric group, it may show fluorescent. But all dye molecules which observe may not be fluorescent also. Okay?
May color, they may give color, but they
They may give color.
may or may not show fluorescence.
Fluorescent, yes.
Okay, ma'am. Thank you, ma'am.
Now also you can search which molecules are UV visible, can show UV visible absorbance, but will not show fluorescence. You will find many. They will be colored, the molecules which are colored but will not show fluorescence.
Since ma'am, methyl orange, like meth
Yes, yes. Good example. Methyl orange. It is colored, but it will not show you fluorescence. Phenolphthalein. Today we discussed about phenolphthalein, right?
ma'am, it has not a rigid fused ring system.
No, no, no. Phenolphthalein, it is not having conjugation, but it is absorbing. It is colored at certain pH.
At pH greater than 7.
pH. It is pH sensitive and it is colored at certain pH, but it is not fluorescent because it is not having conjugation.
Yes, ma'am. Phenolphthalein actually it is pink color in basic medium, uh,
Yes.
greater than 7, but it is not fluorescent.
No, it
It
is not fluorescent.
observing the.
Today, today class, you saw today class I was telling regarding phenolphthalein. Here, I was
Yes, ma'am.
explaining this part.
Yes, ma'am. Yes, ma'am.
You were in or you were not there?
Yes, I was there, ma'am.
Yes. You see, the fluorescein there is conjugation. However, in phenolphthalein, the conjugation is getting breaked.
Yes, ma'am.
Okay, due
Yes,
to lack of conjugation, it is not showing you fluorescent. However, it is showing a color. So the thing is, in general, uh, always there is certain rules and certain things, but provided to every rule there is also limitation. So that is the thing.
general from general observations we can just keep some things in mind to expect that it will show
Expect that
fluorescence.
it is fluorescent, like it should have a
You,
conjugation, like it should have a rigid structure. Okay, like here I was showing, if it is having electron donating groups attached to it, then it may enhance the fluorescence. If withdrawing groups are there, it may reduce the fluorescence. So like that.
yes, ma'am. Yes, ma'am.
Okay.
Yes, ma'am. Thank
Okay
you.
then. So for today we are closing. Then tomorrow we'll come with another part. So now I am stopping the recording. Can
Ma'am,
you
am
hear?
I audible? Hello.
Uh-huh.
Ma'am,
Yes.
can you provide us the recording part of the today class so it will be better for us.
Actually, these all you can contact the coordinators of the class. You can contact them regarding the classes, recordings, or materials, or any type of this practical classes or theory classes. You can contact them. I
Actually,
mostly.
ma'am, thing is that during the class there are sometime network issue or so it will be better if will we get it and later on will we see that recording part. It will be better for us.
It will be better for us. That I
Okay,
understand,
thank you.
but I can. So,
Okay, thank you,
just,
madam.
hmm, just
And
as much.
ma'am, actually, one thing I would like to tell you that I have completed just graduation. Then, after
Okay.
a long time, I am doing this course, and for now, it is very difficult to catch all the things. So,
Very
if you will
difficult.
be yes, ma'am, if you will be explain everything to easy way, so it will be better for us to understand. And ma'am, actually, frankly
But
speaking,
but
I am not
but
doing.
frankly speaking, Mahendra Sahu,
Yes, ma'am.
that
Yes, ma'am. I'm from
we
Odisha, madam. You can
okay.
also. Uh,
But the
yes.
thing is, the spectroscopic method which we are
Yes.
studying now
Yes.
is not a normal line of chemistry. It is coming here. Normal
Yes,
reaction,
ma'am.
normal chemistry we are not studying. It is a
Yes,
tool
ma'am.
to analyze all the things. So it is really a difficult topic. In the past class itself, I made everyone clear that among the four, this will be very difficult, but I am trying my best to make you understand and to feel about the systems and things. While going further, doing further study only, you can able to understand very clearly, but I am explaining in the simplest way. More than this, I can't make it to simplify it to make you understand.
Yes, ma'am. I can understand. But, Ma'am, if you will be give us some suggestions, we will be get good mark in at least get good score. That is, ma'am, we want. Actually, I am not doing the master's course after complete
See, you can
graduation.
do. See, you can do one thing. These materials are already available in the IGNOU website. You can
Yes, ma'am.
download that, and there are many questions. I am just discussing with you, and I am seeing the questions also. That questions are also there, and you can go to like 5 year study material questions. Then you can prepare in that way. And for
Yes,
this,
ma'am.
for this, you can always contact your coordinators, respective coordinators, and you can also clarify with them. There is no harm
Okay,
in that.
okay, ma'am.
All are ready to
Okay.
help you.
Thank you, madam.
Okay.
Thank you, ma'am.
Nandini, thank you. And Ojas, can we detect arsenic in water using photoluminescence techniques? Yes, we can do. We can do. There are various literature while going through my PhD scholars work. I had seen arsenic detection has also been done. Arsenic, cadmium, fluoride, that also you can do. As I was telling you, if that metal is not fluorescent in nature, then what you can do, you can add a fluorescent tagging. You can do, you can attach a fluorescent molecule to that, but provided you need to see which can attach in a better way. Okay, then you can study its arsenic contamination. You can predict through fluorescence luminescence technique. Okay. Okay, then. No more question. Thank you very much. So, see you again tomorrow.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Thank you all.
Thank you, ma'am.